Over a 50-year period, a coal plant burned a total of 84 gigatons of total coal. If currently peak demand is 400 gigawatts and demand growth has followed a continuous exponential model with alpha of 1% per year, what's the efficiency of the coal plant? And we were given a conversion rate of 10,000 BTU per pound. So the givens, we have a time period of 50 years. We have a weight of coal for us, so gigatons, mass of coal, I guess, 84 gigatons. We were told current peak demand is 400 gigawatts, so that's a power. Power is 400 gigawatts. Alpha is 1% per year. Those were the givens. And we were asked to find the efficiency of the coal plant. So the solution method is, remember that if we have a energy conversion process, it's going to produce some output energy, it takes input energy, and the efficiency is the ratio of the output to the input, E out over E in. So that's what we're being asked to calculate. Just a reminder that it's for coal. So we need to calculate both the output energy of the coal plant total over the 50-year period, and we need to calculate the input energy of all the coal that was burnt by the plant over the 50-year period. So I'm going to handle the top of that fraction first. We know that if we have a demand plot, our continuous exponential function looks something like this. We were saying we're analyzing this over a 50-year period. And in this situation, we were told what current demand is at the end of the 50-year period. So we were told what P50 is. 400 gigawatts. We don't know what the initial demand was. So we can solve for initial demand because we need it if we're going to integrate this function. Remember, what we're trying to figure out eventually for the top of this fraction is E out coal, and the formula we have for that is that we take the initial demand, we divide it by the growth rate, we multiply it by e to the alpha t minus 1. So that's the integral having been done for you. It's the result of calculus. And to do that, we need P0. We don't have that. We have P50. So if you understand this plot, you know that this plot comes from the formula P in the future equals the current demand. So the future demand is equal to the current demand times e to the alpha t. And so I can solve that for P0, right? P0 equals P over e to the alpha t. So I was told that was 400 gigawatts. 400. Gig is e to the ninth. And then we're going to need to divide that by e to the 1%, so 0.01 per year, times 50 years. This will be unitless down here because they cancel, so we're just left with a initial power. So if you do that, you get the initial demand was 242.612 gigawatts. So now I can take this number and plug it in to that formula. So E out of the coal plant over that 50-year period is going to be 242.612 e to the 9th watts divided by 0.01 per year. And then I'm going to multiply that by e to the 0.01 times 50 minus 1. And we'll see that we get an answer of watt years here. So we get 1.57388 times 10 to the 13th watt years. This is all unitless. I didn't write the units here because they cancel. I left them here because we get watts divided by 1 over years, which is watts times years. That's what I have there. So that's E out in the coal. That's the numerator there in this fraction. So next we need to know what the input fuel energy is to get the denominator. So the input fuel energy, we were told that it was 84 gigatons. So 84, just like a gigawatt is e to the 9th watt, the gigaton is e to the 9th tons. So we got 84 times 10 to the 9th tons of coal. That's how much mass we had in. We need to now convert that over. We know the conversion rate was given to the problem in the problem statement of 10,000 BTU per, is that a per pound? Yeah, per pound of coal. So that won't cancel. We need to add a conversion factor between pounds and tons, so I need pounds to cancel. There are 2,000 pounds in a ton. And so now I get pounds cancel out, I get tons cancel out. I should have wrote coal right there. The coal cancels out because that's 10,000 BTU per pound of coal. So if I do all this multiplication, all the units except BTU cancel out, so I'm left with BTU. So my input fuel energy is therefore 1.68 e to the 18th BTUs. So I can write my efficiency equation as the output energy that I calculated here in watt years divided by the input energy that I calculated here in BTU. So that's 1.57388 times 10 to the 13th watt years divided by 1.68 e to the 18th BTU. Clearly I can't do a direct division right there, and so I need to convert the BTU over. I'm going to do that with a two-step process because I know BTU per watt hour. So there are it's about 0.3, but 0.293071 watt hours per BTU. So that's going to put the denominator here in watt hours. And then I'm going to turn the numerator into watt hours as well. And I can do that because there are 8,760 hours in 1 year. So if I multiply the numerator by 8,760, my years are going to cancel out and I'll get watt hours. So throw that all into your calculator. You're going to find that this coal efficiency is 0.28, which is 28%. So the plant that we're analyzing has a 28% efficiency.